to show you that a very large exponential expression, 20 to the 15th minus 1, is equal to some multiple of 61. We'll just say 61m, where m is a positive integer. Now this divide statement is it's equivalent to this statement right here. It's 61 divides the quantity 20 to the 15th minus 1. We want to show that's true. Okay, now I'm going to recharacterize it as a modular arithmetic statement. Modular arithmetic, this would read 20 to the 15th is congruent to 1 mod 61. Very same thing. It means exactly the same thing. It means that 61 divides the difference of 20 to the 15th and 1. The joy of doing modular arithmetic is you never have to know anything about 20 to the 15th's real magnitude. It just, everything works out nicely. Now, this very first step is a little hard to motivate. Some of you may understand why we did this, but at least we have mod 61 going on here. Notice that 3 to the 4th is 81. And so trivially, 3 to the 4th is a multiple of 61. It's 61 itself, okay? Now, the reason why, a lot of you may already know the punchline here, there's something called Fermat's little theorem, or the Euler Totient function, that would motivate us to raise both sides of this to the 15th power. And of course, we want to raise this side to the 15th power simply because it's our problem statement. So if we raise the left-hand side to the 15th power, you multiply the exponents and you get 3 to the 60th. See, and this is the whole reason for doing this, if you recognize this form right here. So that's congruent to 20 to the 5th, and again, 15th, excuse me. The reason why I like this so much is it's much like just working with equality. You're actually kind of reducing the notion of divisibility to equality in many ways. Okay. Now, why is this special? Well, there's a gentleman by the name of Fermat, a French lawyer and mathematician, dilettante, proved that as long as p and a are relatively prime, a to the p minus 1 is congruent to 1 mod p. Now, a lot of you may have seen the Euler Totient function. It's the very same thing. You can write this as a. If you know, this follows from Euler's Totient function basically. So I'll write this here. This is my phi function. Phi to the p. Okay, is congruent to 1. My p, and of course, p and a can't be multiples of each other or relatively prime. Okay, but phi of p is just 1. In other words, it's the number of integers less than p that are relatively prime to p. But since it's a prime number, this would be the very same thing as what we have directly above it, a to the p minus 1. So either way you want to think of it, it's still get what we need. All right. Now, so that's the form this is in, right? We're mod 61 and 3 to the 60th. 3 is relatively prime to 61, right? And so this becomes 1 is congruent to 20 to the 15th. Okay? And that completes the proof. And again, this was a shorter part of a harder problem in Sierpinski's 250 number theory problems. I think it was number 7. But anyway, that's, again, what we're trying to prove is equivalent exactly to this congruent statement. And of course, it's mod 61. So that does it. Okay, till next time.